we want to look at the mean value theorem. Now, before we get to the mean value theorem, let's look at a problem we looked at last week. We want to find the max and min values on the closed interval from -2 to 2. Now, if you want to try this on your own, you can pause the video and try to solve this problem on your own. So I'll let you pause the video now. Okay. As we come back, let's go through and solve this. So the first thing we need to do is to find our critical numbers. And to find the critical numbers, you got to take the derivative. The derivative of x is 1 minus 3. Bring down the 1/3. Subtract 1 is x to the -2/3. 3's cancel. So our derivative is 1 minus 1 over x to the 2/3. Now our critical points are places where the derivative is equal to 0. So we want to set this equal to 0 to solve, and where the derivative is undefined. Because we have an x on the bottom, we can see that 0 is a critical point, and 0 works in the original function. We don't have 0 in the denominator anywhere. So now if we solve this to try to find where else we have critical points, this would tell us that x to the 2/3 is 1, as I cross multiply here. Now, to solve this, I can raise both sides to the 3/2. So this is 1, excuse me, not 3/2. Let's just raise it to the 3. If I just raise both sides to the 3, the 3's cancel, and I get x squared equals 1. So you can see for the x, I get plus or minus 1. So there are our critical points. Remember, critical points are where the derivative equals 0 and where the derivative is undefined. So now to find our max and min, we want to go through all of those points. We want to look at the functional value at 2, the functional value at -1, the functional value at 0, the functional value at 1, and the functional value at 2. If we do those, I've already plugged them in, we get 1.78, we get 2, we get 0, we get -2, and we get -1.78. So, our maximum value, we're looking at the y, our maximum value is at the point -1, 2, and our minimum value is at the point 1, -2. So that's just kind of a review of what we did last week. Now, let's talk about the mean value theorem today then. So, to get us started, I want you to consider this. What is the difference between the instantaneous velocity and the average velocity? So if you were driving from Smithville to Worcester, and the cop pulled you over by the barn and said, well, you were going 90 miles per hour on 585. And the instant that he got you going 90, that's the instantaneous velocity. Now, let's say, well, I did 90 on 585 and I did 30 in Smithville, so my average is only 60. It doesn't work that way, right? If you remember, your average velocity is the total distance or total displacement divided by time, where your instantaneous velocity is what happens at that point. So, consider an example. Consider you travel from Smithville to Toledo, which is 150 miles away, and you travel there in 2 hours. What did you do? Well, if you went 150 miles in 2 hours, that means your average velocity was 75 miles an hour. Which what that means is you were speeding. At some point, you were speeding. Now, what if you said, well, my average was 75 miles an hour, but I never went 75 miles an hour? That wouldn't make any sense, right? I think we understand that just by practically speaking, if your average was at 75, at some point, the speedometer on your car had to say 75. You couldn't have been going 60 and then jumped to 90 and your speedometer never was 75, right? That doesn't make sense. And that's kind of what we're going to get today with our mean value theorem. I'll come back to that analogy. Now, before we get started in the mean value theorem, let's look at a more simple, specialized case that's called Rolle's theorem. And here's what Rolle's theorem says. Let a function f of x be continuous on the closed interval a to b and be differentiable on the open interval a to b. So continuous, there's no gaps, there's no holes, there's no asymptotes. You can draw from a to b without lifting your pencil, right? Not a great definition, but it'll get us there. To be differentiable on that same interval means there's no corners, there's no cusps. It's smooth, nice, well-behaved kind of function. Now, if that's true, it's continuous and differentiable, then we know that if f of a equals f of b, and you can see in my graph here, if f of a equals f of b, then there is some number c on that interval such that the derivative is 0. Well, think about what that means. If I start here at f of a, and I eventually end up at b, there has to be some point c where my derivative, slope of the tangent line, equals 0. And if I would go a different direction, I have a different c here, but if I go a different direction and I go down and then I come up, in this case, my c may be over here. But there has to be some point between those two where my derivative is 0. Now, you may have a crazy function that does something like this. And if that was the case, you would have 1, 2, 3, 4, 5, 6 points. But Rolle's theorem, and the mean value theorem we're going to look at in a second, is an existence theorem. It just says if you have these conditions, you're continuous, you're differentiable, and you know that f of b equals f of a, then the derivative has to equal 0 somewhere. Has to happen. Because there's no way to get from this point to that point without having a peak or a valley, or it could be a perfectly straight line. And in that case, it's equal to 0 everywhere. Okay? So that's Rolle's theorem. But what happens if f of a does not equal f of b? What happens if we start here and we end up here? What do we have? That is going to be our mean value theorem. So here's what the mean value theorem says. Once again, let f of x be continuous on the closed interval from a to b and differentiable on the open interval. Okay? So once again, smooth, well-behaved. And what that does for us is we can't have, if I go back to here a second, we can't have things where this goes down here and then jumps up to here, and you're like, well, it's never 0, because you have a big gap here, so it wouldn't be continuous, it wouldn't be differentiable. Okay, so it's smooth, okay? Then this mean value theorem says it's an existence theorem. Doesn't tell us how to find it, doesn't tell us how many of them are, but it says there is at least one c in the interval such that, f prime of c, the derivative at c, is f of b minus f of a all over b minus a. Now, let's talk about our formula here a little bit as we look down here. So first off, I want to look at this side. If you look at that side of the formula, and you have f of b minus f of a all over b minus a, that right there is basically the slope of that line. We're going from the y-coordinate f of b minus the y-coordinate f of a divided by the at b minus a, these subtracting x's. So that is the slope coordinate. Now what this is telling us is if we have some function that can do anything, this function may come up here, and it may come down here, and it may come up there. What this is telling us is there is some value c such that the derivative at c is equal to the slope of the tangent line. So there's some point, let's say right there, where my c has the slope of the tangent line is equal to the slope between these 2 points. And in the way I drew this, we actually have another c back here. So we have 2 points. Now, you may have only one. Your graph may go like this and come like this. And in that case, you may only have one. But it's possible to have more. And if you have a crazy graph, you may have more than that. But all this is saying is if you go between a f of a and b f of b, right? This is the point b f of b. And down here, this is the point a f of a. If you go between those 2 points and you find the slope, and that's the right side of mean value theorem here, there has to be some point on the function where the derivative at that point, the slope of the tangent line at that point, has to equal the slope between these 2 points. So that's the mean value theorem. Now, a few things. First off, what about this? If we said, well, where's c? This is Rolle's theorem, actually. The derivative, the slope of the tangent line between these 2 points is 0. Well, where's the c where the derivative is 0? And you would say, well, at 0, the derivative doesn't exist. But we can't consider this, because if we go back to our conditions, it has to be continuous and differentiable. So this is continuous. We can draw the absolute value, but this is not differentiable. This doesn't apply. So you have to have a continuous and differentiable function for this to work. So let's look at an example. So find each value of c from 0 to 3 such that it satisfies the mean value theorem. Okay. So by our mean value theorem, we have, let me write it up here, we have f prime of c equals f of b minus f of a all over b minus a. So first, let's do the right side. And if I put 3 into here, I'll have 3 minus 0 minus 0. And if I put 3 in here, 3 squared is 27. And so I get 36 over 5. I had done this ahead of time, which that gives me negative 12/5. Now, we now need to find f prime of c. So we find our derivative, and our derivative, we bring down the 3, is 6/5 x squared minus 4x. So what we are looking for here with the mean value theorem is what values of c, and I'll write it this way, 6/5 c squared minus 4c, what values of c will give me negative 12/5. So this is just a quadratic. So we'll set this equal to 0. Now, we can then solve that, and we could easily do that on the calculator. If you want to do it on the calculator, you know, the easy way to do that would be to go in and graph 6/5 x squared. We're not really worrying about trying to know how to solve quadratics. Now, if you can factor something easily, let's do it. But if not, if we graph this, we can see we got an answer here at about, and I have them written down here, about 0.8 and about 2.5. We can find those on our calculator, and if we wrote those down, we would get 0.785 and 2.549. Okay. So what we have found is at these two values, if you put those into the derivative, you equal this value, which comes from our formula over here. Okay. Now, the mean value theorem is actually really important as we go forward. Oh, here's the graph. Let me go back to this. So here is the graph of this. And we are at 0 and 3, right there. And if I connect the dots, there is the slope, the line between those. And if I go at, it was 0.78 right there. So right about there is a line parallel to that. And 2.4 right about there, you can see those are the 2 points where the slope of the tangent line is the same as the slope of the line between the 2 points. Now, as I was saying, one of the things we're going to use the mean value theorem for is we're going to prove a couple of corollaries, which are going to help us later when we do some more stuff in the rest of this chapter. So, these are not hard corollaries, and I want to use this opportunity to kind of show how we could prove these, given the mean value theorem that we know is true. And the first one says, if the derivative equals 0 at every point of an interval, then our function has to be a constant. Which makes sense, right? If you take the derivative for a whole bunch of points and they always equal 0, then your original function is probably a constant. So let's talk about what we want to do. So what we want to show here is if we pick any 2 points in our interval, and the way I'll write this is like this, and if you turn around, look at the back wall, this is for all A and B contained in the interval. So for all points in the interval, f of A equals f of B. So we want to show that's true. Okay? So what are we given? We are given that the derivative is each point, the derivative of each point is 0. So we are given that the derivative equals 0 at all the points in the interval. Well, what does that tell us? Since we have a derivative, that tells us we have a derivative. That means it's continuous. That means it is differentiable. And so by the mean value theorem, we know there exists a C such that the derivative at C equals f of B minus f of A all over B minus A. Because we have a derivative at every single point, we know it's continuous, we know it's differentiable, so there has to be some C that satisfies the mean value theorem. But what do we know about C? The derivative of that. C is in the interval, right? So this is in the interval. Well, we know the derivative, f prime of C, has to equal 0. That's what's given. The derivative at any point, and I wrote this wrong here, I realize, this right here, should say x, for any x in the interval, equals 0. And now, if we have a fraction that equals 0, we have said numerous times, if you have a fraction that equals 0, that only works when the numerator or the top of the fraction equals 0. So we now know that the top of the fraction has to be 0, which then implies, once again, that f of a equals f of b, and that's what we're trying to show from the beginning. So that's how we can prove this corollary. Corollary basically is just a easy theorem to kind of prove that is based on a bigger or more important kind of theorem. Okay? So let's look at the second one. The second one says, corollary 2, if the derivative of f and the derivative of g are equal at every point in the interval, once again, means they're continuous, means they're differentiable, so we can use the mean value theorem. Then there is a constant c such that f of c equals such that f of x equals g of x plus c. So let's once again try to prove this. We want to show that f of x equals g of x plus c. So what are we given? And let me just say, you are not going to have to do these proofs. I like to show you these proofs so you can see kind of what's coming for those of you that got a future in more math doing these kind of stuff. I'm not going to ask you to do these yourself. So we want to show that f of x equals g of x plus c. So we are given that f prime equals g prime. Now, here's where the part we're going to kind of make something up, that we're going to pull something out of thin air. So let's say we're going to create this new function, which is f of x minus g of x. Just making that up. Let's say we have these two functions. Let's just make a new function where we subtract them. Now, consider the derivative of that. Well, if we have a subtraction, we just take the derivative of each part. So we get to there. However, we know from up here that our derivatives are equal, which tells us that our derivatives is equal to 0. But if our derivative is always 0 for every single value of x, by corollary 1, back here, we know that this has to be a constant function, which means this has to be equal to a constant, which tells us that f of x minus g of x equals a constant, and I'm running out of room. So therefore, we know f of x equals g of x plus c. We have just proved what we were trying to show by using our corollaries. So the mean value theorem is something that's going to be very useful going forward. And what that means that we just proved is something like this. You can have two functions, and if both of these functions have the same derivative, we know the original function is only going to differ by some constant. That's what this corollary proves. We're going to use this corollary as we do more later throughout the rest of this chapter. So this mean value theorem is really something that we're going to use to set up the rest of what we are doing throughout the rest of this chapter. All right, you are now able to do your homework, section 4.2, over the mean value theorem.